Okay, so again, this is a second order equation. The right-hand side is not something that we know how to annihilate. So the only other method that we've talked about is variation of parameters. So that's in section 6.7. And can you guys remind me what's the first step for the variation of parameters?
Find YC.
Right, the same as the annihilators. You find the complementary function first. Okay, so to do that, what are we going to write down
R
first?
squared minus R plus 17
R squared what?
minus 8R, sorry, plus 17
Okay.
equals 0.
Equals are good. And now that one does not factor nicely, but we can find the roots using the quadratic formula. So some of you probably have been already working on this. So take, change the sign there, plus or minus b squared is 64, minus 4ac all over 2a. This is worth checking and double checking a couple of times. Because you want to have this right. You really need to have that right. So make sure that some people have made mistakes, just simple mistakes with the characteristic equation. So you want to definitely... Nobody wants to be on the internet. Be famous on YouTube tonight. Okay, so that's the equation. Now 8 over 2 is just 4. And then what's the square root of 64 minus 68? 4i. Well, the square root of 4 though, right? Which is 2i. And then I have to divide that by 2. So I get 4 plus or minus i. Okay, based on that, do you know how to write down the complementary terms?
Yeah.
Okay, what's it going to be?
C1 e to the 4x cosine x
Okay,
plus C2 e to the 4x sine x.
good. So there's the complementary function. Only 2 terms because it's only second order. So only have 2 roots there. All right. So the next thing is,
Wronskian?
do you guys know the formulas?
Yeah.
Do you remember them?
Yeah.
U.
So we need the U1 and the U2, which have the Wronskian in them. Let me just write down the formulas now. So the way I remember it is the subscripts are swapped. So if it's U1, we write Y2, capital F over W, and we change the sign on that one. Okay? And then U2 is positive integral of Y1F over the Wronskian. These are all with respect to X. And no minus sign on that. Okay? So we derived that in class. You don't really need to know the whole derivation, but I do want you to know the formula. And then the other thing, of course, that you have to know is, well, once you find these 2 things, what is the particular solution? Can somebody tell me?
U1 y1 plus U2 y2.
Right, so basically it's just, you just take C1 y1 plus C2 y2 and you change it to U1 y1 plus U2 y2. And then we're going to find these things. These problems are usually pretty simple if you know the formula. So, so that's what we have. So it might be helpful to actually clarify, this is going to be y1, and this is going to be y2. If you wrote them down in the opposite order and you had the y1 and the y2 switched, you would not be wrong. It would just be that then your u1 and u2 would also end up getting switched. And that's fine. Okay. So I tend to put cosines first and then sines, but it totally doesn't matter. Okay. So Sergio wants me to find the Wronskian. This is the W. It's the Wronskian of what?
Y1 y2.
Huh?
Column. Just put them in the column.
I'm sorry?
Fine.
Okay. What'd you say, Sergio?
Just put them in the columns and then find the first derivative to get a square matrix.
Okay. Yeah. This is chapter 6. Right? Chapter 6 Wronskian. So we're gonna put. I need a bigger. I'm gonna need more room here because I can tell I have to use a product rule. Okay. So let me make this a little bigger. It actually won't be that bad. So we have e to the 4x cosine of x and e to the 4x sine of x. And I'm going to use a product rule to take the derivatives. So I'll get negative e to the 4x sine x plus 4 e to the 4x cosine x. That's still not big enough. The second one, wow, will be e to the 4x cosine x plus 4 e to the 4x sine x. And we just have to work that out, AD minus BC. By the way, on this one, do not choose numbers for x on this one. On the ones where you're checking linear independence, that's fine. But right here, you need to actually get whatever the function of x is. Okay, so we're not just trying to see, we already know it's not 0. We're not trying to see whether it's 0 or not, like we were on some of the earlier problems. We just want to know what is the formula for it. So I'm going to write down e to the 4x cosine x times the quantity e to the 4x cosine x plus 4 e to the 4x sine x. Okay, and then minus e to the 4x sine x times negative e to the 4x sine x plus 4 e to the 4x cosine x. It takes just a little bit of patience to get this right. Now I'll just multiply it out. E to the 4x twice gives me e to the 8x. Actually, every single term will have e to the 8x in it, so I'm just going to pull that out, leaving me with cosine squared plus 4 cosine x sine x. And here we have plus sine squared. Excuse me. And then minus 4 sine x cosine x. And these terms are going to cancel. And cosine squared plus sine squared is just 1. So it's just e to the 8x. Very simple. Okay? So just get e to the 8x out of all that mess. That's the Wronskian. Okay? So far so good? So now I'm ready to pretty much put everything into my formula for U1 and U2. So U1 equals negative the integral of y2, which is e to the 4x sine x, times f. F is this thing here. I'm going to go ahead and use the fraction form of it. So that would be e to the 4x over sine of x. And then I put the Wronskian on the bottom, which was e to the 8x. Wow, doesn't get any easier than that. Everything cancels. You just have a minus sign, right? Antiderivative of 1 is just x, so it's minus x. Do I need a plus c on that?
No.
Not when we're looking for one particular solution. We don't need the whole family of them. We just need one solution. So it's just negative x. Yeah?
Quick question. I know you changed it to e to the 4x over sine x. I used to know all the trigger names, but I didn't anymore. So on the test, are we going to be expected to know the trigger identities?
You probably should know. If you came up and asked me during the test, I'd probably tell you.
Okay.
I'd probably tell you and give you a little smirk or something. But you technically should know that, but yeah. So anyway, I don't want that to be the reason you can't do the problem. I don't want somebody losing, a 12-point problem here or something like that, just because they didn't know how to convert it. So more than likely, I would give it to you. I might take off a point or something on the spot. Yeah. Okay, so that's U1. And then U2, surely this one's going to be a little harder. This is the integral of y2, which was, I'm sorry, the integral of y1, which is e to the 4x cosine of x, times e to the 4x over sine of x, times e to the 8x dx. And again, it simplifies considerably. It's just the integral of cosine of x over sine of x. All the exponentials go away. And that's actually the integral. That will be in your table because that's cotangent. But if Sergio doesn't know that, then he can still do a u substitution. because the denominator u is the sine of x and the derivative of that is cosine. So it's really the integral of du over u. So you could still get away with it. It's ln of the absolute value of sine of x. Okay. We got that. So then our particular solution, y sub p of x, is u1, which is negative x, times y1, which was e to the 4x cosine of x, plus u2, which is ln of absolute sine x, times y2, which is e to the 4x sine x. Make sure you write that down. Okay. Look at that. And now, my final answer would be what?
Y of x equals y c of x plus y c of x.
Right. Y sub c plus y sub p.
And c above.
Right. So, instead of wasting time writing the whole thing out, because it will typically be pretty long, instead of doing that, you can just say that you're just adding the complementary and the particular solutions, which you calculated above. Okay? So it's just this one plus this one. Make sense? So the main thing here is you need to be able to recognize when to use variation of parameters. Look at the right-hand side, that's the key, and the order of the differential equation. So you should know when to use it, and you need to know these formulas. There's really nothing else in this section that I can throw at you that would be worth asking. Okay? But I mean, chances are good that I'll ask you to do one of these just to prove to me that you know how to do it. If you get stuck on the integrals, could be, first of all, it could be because you made a mistake. Because I'm not going to ask you to integrate something that's unreasonable. It's either going to be in your table or it's going to be a simple one. If you didn't make a mistake, but you're still not sure how to do the integral, chances are you're not going to lose a lot of points for screwing up the integration. If you know the process over here, that's going to be the bulk of what I'm looking for. Okay? So. All right. Everybody okay with that part? Okay. Let me do another problem. Do you want me, there's two or three things here. I was going to go back to chapter 7 again. Are you guys doing okay with this defective linear system thing that we just learned?
Can we do an example of that?
Yeah, this is where you have the W's that we learned about on Wednesday.
Yeah.
I have an example of that here somewhere. I think it's number 4 on the sheet here. Yeah. Okay, so number 4 just says solve x prime equals ax, where A is the matrix -2, 4, 0, -1, 0, -1, -3, 2. And there's an initial condition given as well. So this has a lot of aspects to it. Yeah.
On here you didn't put the little arrow on top. Does that matter?
And put the arrow on top of what?
Of like the X?
Oh, that's because I never do in typed up stuff.
Oh, okay.
I always use a boldface.
Okay.
So the boldface in the notes is the same as arrow on top here. Yeah. Okay. So you see this problem, what do you do first? Determinant of what?
A minus lambda.
Okay. I subtract, well, a minus lambda I, right?
Yeah.
We're not going to do a minus lambda because that's a matrix minus a number. But I know what you mean. So we're going to subtract lambda off of the diagonal. So we're going to get something like this. have 6 different choices here. First row, second row, third row, first column, second column, third column, and this is one that you want to do, make a good choice. What do you think?
Row 2.
Row 2 this time, right? So please be on the lookout for that. I'm not going to give you something that you have to do in an unreasonable fashion. So this would be a good one to use. So the reason I like row 2 is that when I cofactor expand it, I don't have any, I only have one term. And we know that it's going to be with a plus. So it's a plus there, so it's just literally as is, minus 1 minus lambda times, use parentheses, parentheses are your friend here. We get negative 2 minus lambda times 2 minus lambda, and then plus 4. So this is negative 1 minus lambda times, okay. Then this one we have lambda squared. What's the rest of it going to be?
Minus 2 lambda plus 2 lambda minus 4.
That's fine.
Minus 2 lambda plus 2 lambda minus 4 plus 4. It's all gone. Everything else cancels. So your eigenvalues are 0, 0, and negative 1. And if they come up multiple times, you should write them down multiple times so that you know that. Okay? Does this mean the matrix is defective? It does not. It might be, but it doesn't have to be. Does it mean that this matrix, that's a side question, does it mean that this matrix is invertible? No, it's actually not invertible, right? Because remember the product, going back to my little hint from earlier, if I multiply the lambdas, I get the determinant. Well, if I multiply these together, I get 0. So the original matrix is not invertible, but it still might be diagonalizable, or in other words, non-defective. Everybody knows diagonalizable and non-defective are the same thing, right? Just 2 words for the same thing. Okay, so which of these lambdas do you want me to do first?
Negative 1.
Pardon?
Negative 1.
You want to do negative 1 first? If I ask the question, is it defective or not? Then which one would you do first?
0.
The one that might be a problem, and you check that right off the top. But I'm okay with what you said, Sergio. You want to try negative 1 first because we're being asked to solve the system. We're going to have to deal with all these lambdas anyway. So I'm going to go with. I'm going to go ahead and do that. I'm going to use negative 1. And what do I need to find right now? Right, the null space. And we have to be very careful as we're doing this calculation. I'm going to add 1 to the main diagonal. So I'm going to get negative 1, 4, 0, 0, 0, negative 1, negative 3, 3. That matrix has to be not invertible, and this one clearly is not invertible. And this one, we really do need to kind of row reduce it. So for the first time, we've been here for almost 2 hours and I haven't done an ERO yet. I'm going to do an ERO right now. Actually, let's just change the sign on the first row. So 1, 1, negative 4. And then I'm going to add that to the bottom row. And, well, of course, I have a row of zeros down here. Yeah. So basically adding these two together, I'm going to get 0, negative 2, negative 1, I believe. Which I'm going to change to 1, 1, negative 4, 0, 1, 1 half, 0, 0, 0. So that's about as much as we're going to do. Guys, you don't need to dwell on the EROs. You don't need to explain your steps so much. Just don't get careless with it and get on too much of a hurry that you make a mistake. Remember, if you work this out and you don't get a free variable, what does that tell you?
Non-defective. No, defective.
If you don't get a free variable here,
Wrong is wrong.
it means you screwed up. That's what it means. Because you are working with one of your lambdas. We're not trying to decide right now if it's defective. The defective issue is going to be over here. I'm working on this one. But the point is, if I don't get a free variable, then that means I didn't have a null space defined, which means I must not have had the right lambda, right? So I better go back and check again. Right, and you guys are gonna have a lot of time to do that, because I'm giving you the full time to take this test. So please, if you don't get a free variable here, that's a major tip-off that something is wrong. Do you have a question?
Why did you go all the way there? Can't you just stop here?
Pretty much I could have, yeah.
Is that okay with you?
I mean, it's just, I prefer to start finding my free variables from here, I guess. So z is free, okay? And then y, looks like it's negative 1/2 t. And then x is, x plus y minus 4z equals out. So x is 4z minus y. 9/2 t. I'll look this up, make sure.
Yeah.
And that's not that bad of a number, but yeah, that's actually fine. However, what I'm going to do right now is I'm actually just going to multiply through by 2. So I'm going to get 9, negative 1, and 2 for my vector. You don't have to do that. And it will not affect your initial solution later, because you're going to have a constant that you're going to solve for later. If I had left this as half as much, then the constant that I'm going to find later would be twice as much. And so they would cancel out. Does that make sense? Everybody see how I got this? I just took this is really this vector, but I don't like fractions right now, so I'm just going to double everything. I know that if I double an eigenvector, I get another eigenvector. Ooh, that might make a good test question. If v is an eigenvector, prove that 2v is an eigenvector for any multiple in terms of like the theoretical stuff. Okay, so we get that. So what do we do next?
Do our first solution,
Okay.
x1.
Oh, and I'm, can somebody move, Curtis or Sergio? Without even thinking about it, I wrote too far off to the right. So if you could just show that.
Just like flash it.
Yeah, so here it is. This is the eigenvector, 9, negative 1, 2, that corresponds to lambda equals negative 1. Okay, thank you. Now I'm going to come back over here. Yeah, I should have come back over here originally. Thank you. Yeah, if you can just kind of keep it centered on these first two boards, that's
Yeah.
mainly what I need. Okay, so my first solution, somebody tell me what it's going to be.
It's going to be e to the negative t,
Okay?
9, negative 1, 2.
Perfect. Okay?
We don't need the c1 in front of that, right?
Not yet, no. We're going to get to that later. Are we good so far? Okay, so now let's do the other eigenvalue. Lambda equals 0. So that means we're just looking at the null space of A itself. Null space of the actual matrix as is. And there it is. Okay? Now if you can of course row reduce this one. Tell you what, I'll go ahead and do that. So the first, I'm going to switch the first row, I'm going to put the last row first and change it to 1, 3, negative 2 so that I get a 1 in the top left corner. And then I'm going to change the middle row to 0, 1, 0. And then I'm going to put the bottom row, or the top row down to the bottom now. So negative 2, negative 1, 4. And now I am going to take 2 times the first row and add it to the third row. Okay, so I'll get 0, 5, and 0. Actually, hold on a second. This is fine, but we should have already known right here that this matrix has to be not invertible. So we actually know that one of these rows must be cross-offable. Don't quite know how to say that. But the first two don't need to be crossed off because they are Li, right? So we actually know this row could go. And here we actually see it because it's a multiple of the second row. Okay? Okay. So Z is free. Y is what? 0. Good. And then what is X? 2t. So what is my vector in this case? 2, 0, 1. Okay. At this point, do we know, is this matrix defective or not effective? We do know. And what's the answer?
Because we didn't get 2.
Only came to 1.
Lambda shows up twice, but only gave us one vector. That's because we only got one free variable. Yeah. Okay. You know what, guys? Just so you know, and I don't want you to jump steps that you're not comfortable with on the test. I would rather have you do this and get it right. But just looking from here, you can already see from the middle row that y is 0. As soon as y is 0, then the middle of the column becomes irrelevant because those numbers are going to be multiplied by 0. So then you just look and you see, yeah, these two are multiples of each other, and cross one of them off, and then you just do your little switch trick again. Switch these two and change the sign of one of them, but you're doing it with X and Z, with the Y in the middle. I don't want you playing those games if you're not comfortable with it. I would rather see you work the whole thing out. It took me a number of tries of teaching this class before I even kind of got to the point of doing this, regularly. So it's okay if you don't want to, jump that fast. But we do get a second solution here. X2. What is X2?
2, 0, 1.
Where's the exponential?
It's gone. It's 1.
Yeah, it's a little deceptive, isn't it? It's a little deceptive. There is no e to the anything.
Well, there's a 1, but
If you drop this feather in, it's just going to sit there. If you drop it in at that spot, there's no t. Doesn't matter what time it is, it's always there. Okay, so we now need to come up with another solution. We need 3 of them. We've got, well, here they are. We've got one solution here, and we've got one solution here. To get one additional solution, now we need to use the W's. Oh, I'm erasing my initial question. Hold on. Don't need this anymore. Okay, so do you remember how to come up with the third solution?
You do the lambda c.
I like to write down the form of it first. It's just the general form, e to the lambda t, w1 plus t times w2. This is what we just went over on Wednesday. Now in this case, the lambda is actually 0. So we're not going to have an exponential piece this time. It's fine. So if you remember, I don't know how many of you like the diagram, but I'm going to draw it again. You start, you're going to choose w1. You're going to apply a minus lambda I to it to get w2. And then, the second time you apply it, you need to get 0. So you need to choose a vector that will survive a minus lambda I, but not survive a minus lambda I squared. Now in this case, lambda is actually 0, right? So we're actually talking about just multiplying by a. So we actually need to calculate a squared. I prefer to do that first before I start trying to choose anything. So this is a right here. I need to square that. Maybe somebody will let me just write down the answer. Find it, that is. Yeah.